Hello.
Hello.
I assume you hear me well. Okay, it looks like my camera also works fine. Although I don't know if it would be needed.
Mm, it would be helpful to have it because if you wanted to speak up during the presentation, usually you should turn on your camera before speaking up.
So, which chat we using? We use. I see that this is Bridget between BBB and Matrix.
Yep. At least in my web browser, it is in left upper corner. Can you see me? You see me? Okay. Peter, can you see me?
Right now, yes. Like it took some time.
No, it works with a delay. Thanks.
Okay. So how is I assume that because I talked with Richard about LVFS FWPD and I assume like if he didn't get the pass, so he would not be able to join. Is that
Yep.
correct?
Yep.
Okay.
It's that correct.
It's not very good, but anyway.
Yeah, that will be said. We will start in 5 minutes. Okay, let's get started. So welcome everyone in the Linux Plumbers Conference in 2021, and in particular in System Boot and Security Micro Conference. At the beginning, I would like to get you familiar with what will be happening in our room and what are the rules here. So at the beginning, I would like to thank you, our sponsor, our diamond sponsor, Facebook, our platinum sponsor, IBM, and gold sponsors, ARM and Microsoft. Silver sponsors, AWS, and Netflix, and Red Hat. You can gift sponsor, who is Collabora. T-shirt sponsor, VMware. And conference services, for conference services, the Linux Foundation. And in particular, I would like to thank you also, Linux Plumbers Conference Committee, who organized all the event. As far as I can tell, this is a very difficult task, so I would like to thank them to make possible this event happen. So this is very important. Also, I would like to thank Peter from FreeNDEP and Matthew Garrett for doing this micro conference together with me. Peter and Matthew will be helping me to drive this micro conference. Additionally, Matthew agreed to take notes during this micro conference. Also, I would like to remind you about the anti-harassment policy during Linux Plumbers Conference, and in particular our room. And there is also some housekeeping. So we have a very nice tool, Big Blue Button, which runs the conference right now. We have a few tools. First of all, of course, we can use camera and microphones. But if you want to speak up, just first of all, turn on your camera, and then wait until somebody ends speaking, or raise your hand. So this is very important. Also, I would like to ask you to mute your microphone if you do not speaking, to avoid some noises. We have a chat in the left upper corner. This is. I hope that it will run without any issues this time, so we can chat during the presentation and ask some questions. And also, Matthew will be putting some notes into the shared notes. We have 4 presentations in our room. After that, we have some spare time, so we are happy to make some more discussions if you want to discuss some topics related to the system, boot, and security. So I think that's it from my side. Peter, Matthew, would you like to add something?
I believe there is a question from Stuart how he can deliver the presentation for you.
I've uploaded the presentation to the system, so when you start before starting the presentation, I will make you a presenter and turn on your presentation. I hope
okay.
that it will.
So the question is for Stuart if he uploaded the most recent version. Okay, so he mentioned he did uploaded the presentation.
Yes, the most recent one's uploaded.
Okay, that's great.
So the presentation which was on the Linux Plumber conference is the latest one.
Yes.
Okay, thanks a lot. So I uploaded it for you, and I will share it when it comes, when time comes. Okay, so we will start with first presentation in 6 minutes. Daniel Axlens, I will make you a presenter and we'll share your presentation. Are you okay with it? Oh, sorry. Give me a second. Now you are presenter. Hello, Daniel. Nice to meet you. Okay, let's get started. The first presentation will be made by Daniel Axens, working for IBM, and he will be talking about grub modules in Rust. And I'm very excited as a grub maintainer to hear what will be happening with this. Okay, over to you. Thank you. Daniel, you are muted, I think. We cannot hear you. We cannot still hear. Something doesn't work. I think your mic is muted somehow. Nope. Nothing.
How's that?
Okay.
There we go. Okay.
Yeah.
Excellent. I disconnected and reconnected from the audio, so yeah. Right. So grab
No problem.
modules in Rust. I want to just briefly talk about what I'm doing and what I'm not doing. So what I'm trying to do here is to give us an opportunity to discuss how we would go about writing modules in Rust for Grub. I'm not trying to replace Grub. I'm not trying to rewrite all of Grub. I'm not trying to make Rust a requirement for building Grub. These sort of last 3 points sort of go together. I'm not trying to break your backwards compatibility. I'm not trying to break Grub for Itanium. I just want to make it possible for us to write Rust modules in Grub as an option for platforms where we have acceptable levels of Rust support. Just in terms of background for myself, I've been hacking on Grub now for about 2 years, and mostly I'm a C programmer. I'm not yet a Rust expert per se, so that's where I'm coming from. So the big question to sort of start off with is why bother at all? My hope is that this has sort of been addressed by a number of the previous talks in the conference. In particular, we've seen a lot of discussion with the Rust for Linux stuff about squashing bugs related to unsafety and how Rust prevents you from writing those things in the first place. I'm going, therefore, to not reconvince you of that now and use the time instead to hopefully make space for discussion of the things in Rust that we in Grub where I'd like some input from the community. I think for Grub specifically, there are some things where Rust is quite nice. Rust C compatibility is quite good. You know, you can do calls via the ELF ABI. You can call C code. You can be called via C code. One of the things that's quite nice for our purposes is that we don't have a big heavyweight runtime that we need to pull in, which is quite nice. Platform support's quite good, although not perfect. So we can't Rust currently, modulo the work that we heard about earlier in the conference with the GCC front end or the GCC back end. Rust is LLVM based. LLVM supports many but not all of the platforms that we support. So you can't currently build for Itanium, for example, which Rust does support. So that's annoying. What I think might be a solution for us is that we can provide, because of Grub's modular architecture, we should be able to just write both a C version or ship our existing C version of a module and a new Rust version of a module and just compile them based on whatever platform it is that we end up building for and what tools are available on the build machine. The other thing where I want to highlight that I'm standing on the shoulders of giants here is that Rust for Linux has worked on so many of these problems before, and a lot of people have been doing Rust in embedded systems before. So a lot of this will be talking about how we can learn from Rust for Linux and what we want to do based on especially what they've already figured out. I have some slides here that have now been rendered very much repetitive by some previous presentations at Plumbers. So you have a lot of bugs in large C and C++ code bases that come from memory unsafety. For us in Grub, a lot of our, it's only 40%, still very bad, obviously. It would be nice to have 40% fewer bugs. A lot of, we've had a number of CVEs that are just plain memory unsafety bugs. We've had a number that are logic errors, which basically have been forgetting to disable things in secure boot. And we've had a number of integer overflows. I reckon 40%'s an underestimate. The category of logic errors, I think, is not going to grow as quickly as the category of memory unsafety and integer overflow bugs. And also for the CVEs, we didn't assign a CVE to every memory unsafety bug that we fixed. So for example, heap out of bounds reads, we fixed without assigning CVEs because a DOS isn't really relevant to the secure boot threat model. So yeah, we can fix bugs. But I don't want to tell you why Rust is great. What I really want to do is spend some time going through the presentation, going through the code that I wrote that I sent to the Grub mailing list. And then I have a set of questions that my work has raised for me that I want to see if I can get some input from the Grub community on. And I also want to provide an opportunity for people to ask questions about what I've done so far and how it works. So what I'm going to try to do is share my screen. Hopefully this will work. If it doesn't, let me know, because I have got in the slides a bunch of screenshots. So if this doesn't work, all is not lost. So hopefully you can now see, I'll just drag this over to another screen so I can see what's going on. Hopefully you can now see a bit of a Grub makefile.
I can see nothing.
Sorry, no, Daniel.
Not yet. Okay. Let me turn off the webcam and see if that makes it easier for it to catch up. Okay. The slides it is.
It doesn't work, unfortunately.
That's all right. So, can you hear me and see the presentation again?
Maybe you should switch between the presentation and sharing the screen. Maybe it isn't possible to do that in parallel, I think. You tried it?
I don't know how to stop doing the presentation.
At the bottom of the screen on the left side, you have a plus.
Yeah.
And you have to press the plus, and I think that you should see something, share the screen or something like that. Yeah,
I've got a separate screen sharing button, but I think what I'll do, just so as not to get completely bogged down in this, is just use the here are some screenshots I prepared earlier for this precise set of circumstances.
Okay.
So I don't want to look at those because they're actually really boring. What I wanted to start with was something I didn't take a screenshot of. Okay. Yeah, I am using Wayland, I think, but I was sharing a window rather than the whole screen. So who can say? So we've got some stuff in, this is configure.ac. Configure.ac, we say we will support Rust if we provide this Rust target JSON file, which is a file that tells the Rust compiler how to build a Rust binary for this specific platform. So we use this not just to say we're building for x86 or we're building for Power, but to say things like don't use hardware floats, or don't use vector, don't use SSE, those sorts of things. We test for some various programs, and there are other tests in here as well. We check that that the compiler works, basically. We have some horrifying bits of gentpl.py, where we basically look for a make file can now specify a crate and some Rust sources, and because we use, rather than having everything in makefile.am, we have things like makefile.core.def, which gets processed by this script gentpl.py into makefile.am, which is then auto-configured into makefile.in and configured into makefile and then built. We need some extra magic to detect that we're building a crate and to actually build it. It's fiddly and messy, but it mostly works. This is an example of the target.json file that I mentioned before. So this is the one for PowerPC. Most of this comes from Rust's ability to just spit out the target.json file for the target that you're talking about. So most of the first part of this is largely unmodified from just the output of Rust C, the defaults. Where things change a little bit are these features. So we disable AltVec, which is a vector, VSX, another sort of vector scalar extensions, disable hard float. We turn on static relocations, a large code model, and so on and so forth. And we see similar sorts of things. So I have in the series I sent to the mailing list a file for x86-64 EMU, x86-64 EFI, ARM64 EFI, and PowerPC IEEE 1275. Most of them follow very, very similar sorts of things. They're almost entirely the defaults, with just the sorts of things that we detect in configure.ac, so like large code model, static relocations, and various options to disable SSE and vectors and that sorts of things. So they're not they're a bit magic, but a lot of the stuff we can borrow from Rust for Linux, or we can get Rust to generate for us. We have some code. It's a shame I don't have a diagram, I guess, of how this fits together, but we need a little bit of glue code to tell Rust how to interact with Grub. One of the things that we need to tell Rust specifically is how to do memory allocations. Rust just assumes you can allocate memory. So we tell it how to allocate memory, which basically boils down to we get a request for memory allocation, try and determine whether we've got a valid size, try and determine whether we've got a valid alignment, and then just ask grub mem_align for the size. So this reference to bindings, we do the same sort of thing that every Rust project calling into C seems to do, which is called Bindgen, which parses your header files with Clang and generates a bunch of Rust bindings for from those header files. We support building with Clang. It certainly works because I test it quite a lot. I don't know if anyone does it on a regular basis, but yeah, building with Clang seems to work fine. So I haven't had any problems with that so far. And then if you deallocate some memory in Rust, we pass it straight through to grub free. We also need to handle Rust panics and Rust out of memory errors. So one of the things I want to talk about with Rust is a lot of Rust code in the Rust standard library assumes that memory allocations will succeed, and if they don't, it panics. This is probably not ideal for us. We might want to not do that. It's also not ideal for Rust for Linux. And so they've done a lot of work with failable allocations. And as you can see, there are lots of to-dos here. Like we should extract a bunch of information from Like if we've failed to allocate memory, we should print out what sort of memory allocation failure we've got, and we should print out some of the information about the panic. But so far I've yet to hit a panic, so I have yet to test any of these code paths. What's next? So all the grub bindings are extremely unpleasant to work with. It's one of the things that I've tried to do mostly as a demonstration is just to look at what it would look like to abstract some of the C APIs into more idiomatic Rust. Now, as I said, I'm not yet much of a Rust developer, so this is still a little bit hairy. But this, for example, creates this grub command Rust structure, which contains a grub command T member, and then we create a new function on this struct. So you can call new with your name, the function that you want as your command callback, the summary and description. It registers it for you. And then the nice thing about this is we can say when this Rust structure, so you create this grub command, when that goes out of scope, when its lifetime ends, this drop function is called, and so it automatically gets unregistered, and you don't need to do quite so much thinking about that, which is just kind of cute. This is about a minimal example of how we could make things slightly more ergonomic. There is a lot more that we could do. I just wanted to try something to demonstrate some of what could be done. And then I've created a module that just says hello. One of the things that is a constant pain point here is that there is a lot of Rust, a lot of grub that makes a lot of assumptions about what you can do with C preprocessor macros. So I have created at the moment a C wrapper file, which gets linked in, which gets compiled and linked with the Rust static library that gets built. And that wrapper file defines the module license and provides these, a grub mod init and grub mod fini, which hook into some of the build infrastructure to create the module list files, and to do things like make the Rust module get linked into the grub emulator binary, and so on and so forth. So there's a lot of magic that's done with C preprocessor macros. The module itself, this is a snapshot of it. We start here in grub rust hello init. We create this new grub command with the grub command colon new. Takes the name is rust hello. It is the rust hello command. Currently, my summary and description are a little bit lacking. We stash the command that we get back into a singleton, and then we print hello from Rust. And so this function here, we have to say extern C, so it's C ABI compatible, and we say no mangle. So rather than getting, if you're familiar with how C++ renames symbols, similar sort of deal. Rust gives its symbols interesting names. We say don't do that here, so that when you go to load the module, the grub module loader can find the symbol named grub rust hello in it. The command callback itself doesn't need no mangle because we call it through a function pointer, but we do say extern C so that we get the ABI right, and that just prints hello from a command written in Rust, and in something that very much should be cleaned up, returns grub none through this not pretty invocation. And so this, I should have taken some screenshots of it working, but if you look at the series I sent to the mailing list, you can download it and you can apply it. and there's a test, and it works on the grub emu, it works on x86 EFI, ARM64 EFI, and PowerPC IEEE 1264 in QEMU. I have not tested any of these on real hardware yet, but I don't foresee any weird problems there. Maybe that's overly optimistic for me. So that's a whirlwind tour, not quite as whirlwind as I had hoped, but what I really want to do with what's left of my time, and then hopefully in discussion later, is talk about some questions that have come up. So the sort of preliminary question is, do we want Rust at all? I'm going to assume that we do, and if we, if you want to bike shed that, let's bike shed that after the talk. Daniel, did you want to ask a particular question?
No. Go ahead.
Okay.
I thought that we are finishing the presentation, but not yet. Okay.
Not yet. So one question is how much we want to interact with the Rust build system. So in my RFC, I use Cargo, which is what we usually use to build Rust projects, to build modules as static libraries, and then basically you LD add those with the wrapper C object, and that gets built into a module by the rest of the build system. It's okay. It's going to get a bit ugly if the Rust code tries to use compiler intrinsics. Does that get us into GPL compatibility hell? I don't know. Why would it get it? So we have to be careful with stuff that we include in terms of dependencies. At the moment, we have a dependency on a C types library that's used in the binding generation. That's MIT licensed, but there is, if we bypass the cargo thing, then we've got much more direct control over what gets linked in. So yeah, I suspect the way we want to go is to do the same sort of thing that Rust for Linux is doing, and then they are building bits of the Rust standard library, the core and alloc crates into the kernel. So I assume that they've thought about how that works. Some of these are sort of largely sort of technically and bike sheddy. One thing which maybe we want to address is how we deal with this allocation failure through to panicking. So Rust for Linux, I think, has introduced like failable allocs. So rather than having say you're creating a vector, rather than assuming that the vector creation will succeed, or pushing an element to a vector, rather than assuming that that will succeed, it returns a result type, which you then have to check. Maybe we want to do this and maybe we don't. Maybe like an example where this would bite us, for example, is currently we have a bunch of image parsers in Grub. So for example, if you try and parse a PNG that has a bajillion pixels in it, we will parse the header, we will go, okay, you've asked for a bajillion pixels, we will try and allocate storage for a billion pixels, and that will fail. And then we will say, okay, we can't load that image. And that's probably a situation where we don't want to panic. But on the other hand, we could fix this with Rust, or we could just say, maybe let's not allow people to load very large images.
So that's an improvement on the status quo, though, which those are good, but those are good, and obviously what you're talking about is an improvement on the status quo in general. But right now, if we just made it so that if we take it like it is and make it so that it panics on all allocation failures, we've got the same behaviors we've already got.
Well, yes and no, right? Because if you try and load an image that is too large, the allocation will fail, and Grub will just keep going.
Yeah, okay, I see.
Whereas the panic will kill Rust, and that seems suboptimal.
Yeah, yes, I agree. I agree
Yeah.
with Daniel. We should not kill a grab in such a case, I think.
So either we have to be quite cautious about how we write things that make assumptions about allocations, or borrow however Rust for Linux does it, because Linux is really anti things panicking. Surprise, surprise. I wanted also, so I mentioned the preprocessor macros before, so we do a lot of that. So for example, and we don't do this so much anymore because we build all our modules in for secure boot, but once upon a time, you would build in almost no modules. You would create this command.list file based on calls to that. Basically, we'd grab all of our files, pre-process them into a giant file, look for things like register command, and do shell magic to create this list of commands and their relevant modules. And then we'd have a shim that would say, oh, you've tried to invoke this command that's in this module that we haven't loaded. I will load the module. I will replace my shim with the true command, and then we'll invoke the true command. We don't use the C preprocessor in Rust. So we could maybe proc macros in Rust, which is not a thing I understand very well. But maybe we should just enumerate them explicitly. Miguel, did you want to say something?
Yeah. Hey, Daniel. Thanks for being brave doing this. On the alloc, just to clarify, even if you choose to go for valuable allocations or infallible allocations, you can also keep both and choose, depending on which instance, you can have both as well. Because what we basically did was, well, for the kernel, we disallow all the infallible ones. But that's because we disallow them. But other projects can actually pick at the point of use whether they want one or the other. So you can have the default that you prefer, and so you pick on whatever you prefer. Yeah, that's all.
That's good. Yeah, thank you. One of the things that I think is, so licensing, one of the things that I want us to think about as a community with licensing, and I'm cognizant that I'm running out of time, so I will not belabor this. Rust for Linux has done some of the things that we will need to do. So for example, when you're doing bindings, you need to tell Rust what the mapping is between a C type and a Rust type. And that's done with this thing called C types. There is a community C type module. It is, I believe, MIT licensed. It has very good platform support. But if we move away from cargo, this gets more complicated. Maybe we don't want to include MIT stuff. Rust for Linux has got its own C types library, but because it is written for the kernel, it's all licensed as GPLv2, and we are all licensed as GPLv3 plus. Now, the number of people who have contributed to this file and similar sorts of files is still fairly small, and I believe there's probably a willingness to relicense it, but I'm less comfortable asking the Rust for Linux people to do a FSF copyright assignment. I'm not sure if we're still doing that for Grub. So that might be something that we need to, maybe we're happy just pulling in some things from the community under an MIT license. Maybe we're just going to accept that we're going to have to do it ourselves. I don't know what our position on these sorts of things are in fine detail. And that was all of the questions that I had. I apologize that this has taken so much of the half hour to talk about. I don't know if we've got a couple of minutes before the next session is due to start, if anyone wants to pipe up with particular thoughts.
I will tell at the beginning as a Grub maintainer that for sure I want Rust support in Grub. and I think that your approach, yes, at this point looks quite good. Of course, we have to solve a lot of problems which you brought up in the presentation, but I think that I'm happy to start discussion and to try to solve all of them. To be honest, I hope that I will not be killed by many people, but to be honest, at this point, this is not the highest priority for me because I try to recover from the backlog which is on GrabDevel. This is the most important thing for me. But I can assure you that I want to make this part probably not in the upcoming release, but in the next release. I think that it should be a part of a Grab. So from my side, I'm not familiar with Rust, so I'm not able to tell much about it. A few things which I spotted. One question is about the size of the modules. What is the overhead when you use Rust to generate the modules? I think this is quite important, and this question is more important, I think, than for kernel. And another thing is internationalization. Because as far as I can tell, a lot of people translate messages from the C, and I haven't seen any nationalization macros in your Rust examples. Maybe you didn't care, but I'm not sure it is easy to introduce them or not.
So the Rust hello module for that's not for x86 that's for the EMU one. Let me see what it is for x86 EFI. The Rust hello module is 12K. That's compiled with Grab's LTO, but that's also compiled with the core and the alloc crates built in. And if we move those into the Grab kernel, rather than building them into each module will be smaller.
Okay.
So as for internationalization, I have not looked at all. I will make a note. Rust, yeah, I don't know. I have absolutely no idea. So let's find out.
No problem. No worries.
Yeah. I also agree. This is not the highest priority for the Grab project in the short run. And there's obviously a lot of code that my employer would like to get into Grab before it wants Rust to get into Grab. But I think, yeah, it is. And it's also not ready to land just yet. It needs us to bike shed how we're going to do allocations and how we're going to build the modules. But it is great to have you on board with the overall idea.
And any other questions for Daniel's presentation? Peter, go ahead.
Isn't our biggest issue really the thing about having Itanium support and having to implement everything twice?
Yeah, so the thing is, so for me, the driving motivation for this is that we have so many, like Grab does a lot of stuff, like a PNG parser and an HTTP client. And it would be really nice to be able to optionally move those to, or file system parsers, to optionally move those to safer languages. I'm not proposing to implement new features in Rust. And I just want to make the low-hanging fruit for memory and safety less bad. And I think for that, I'm happy if we just keep having multiple, like a C version and a non-C version, a Rust version.
Okay, Jordan, you have a question for Daniel, I think.
Hi. So I have been following the Grub project a lot, but never really enough to want to learn Grub's build system. I'd love to try to write a small Grub module in Rust. When I was looking at your patch, it was hard for me to see which parts were adding Rust support and which parts were just, adding your hello module. If I could see that separated out, or a blog of here's how to write just the grub
Yeah.
module now that we've got the infrastructure. That'd be helpful for me.
Sure. That's very fair. The grub, I have complicated feelings about the grub build system.
Not only you, I think.
There is one problem I need to fix before that, which is that the grub version that I was building with, the Rust version that I was building with, is inserting this stack probing symbol in every module, and that makes that means that the module verifier says the symbol is defined in multiple modules and fails out. I want to. This is not a problem, by the way, if you're compiling for PowerPC. So I do want to solve that problem because that means that currently you can only build one Rust module at a time, which is obviously suboptimal. Once I sort that out, I think, yeah, making it really clear to people how to experiment with Rust modules is probably very helpful, and we will wind it up there.
Okay, we have 1 more minute. Any other questions? Okay, thank you, Daniel, for taking a step for this. As I said, I'm very happy that you did it, and as I said, I'm happy to continue work on this. But we have before that we have other things to solve that quite important. I think memory allocator. So once again, for working on these issues, it is very important for me. And thank you for joining to us, because as far as I can tell, this is quite late for you.
Yes, it is 1:45 in the morning now, but at least at least it's not Friday. That would have been very brutal.
Sorry about that.
My colleagues and I want to run a LPC APAC, so we'll see how we go with that anyway. All right, thank you.
Thank you. Bye. I made you a presenter, and we'll start in minutes.
Where I'm at.
Okay. Start. I would like to welcome Alec Brown from Oracle, who will be presenting firmware and bootloader specification, which we are discussing for some time, some delays, but I hope that will speed up the discussion right now. So over to you, Alec. Thank you.
Thanks. So I'm Alec, a software developer at Oracle, and we've been recently working on development of a specification for some firmware and bootloader logging. To make things a little bit easier, I'd ask if you save questions till after I get to the presentation. It'd make things a little bit easier. And if you do have questions, write them down. We can get back to them after. So to begin with, well, before I get into the background, the main goal of the specification was to develop a logging system to allow for various boot components to send their logs to the OS so users can read them after they've run their course on the boot chain. So a little bit of background on the project. We needed more information for how the platform was set up during boot for the trench boot project. So we started some development, I believe last year, on an early version of the logs for specifically the grub bootloader. And after some discussion, we found that, okay, this can be extended to firmware or shim logs, and we could make it a little more generic for other environments. So we will get into some of the proposals we had. So we came up with 3 different structures on how we think we could store these logs. On the left side, we have a log header, which will be used as a linked list to connect all the log buffers that are generated by the various boot components. And on the right side, we have a specific logging format that can be used for this. In this case, we're calling it the BF log format. We'll be probably using this for the grub bootloader, but it's not a requirement that boot components have to use this. There will be various log formats that a boot component can use, such as the core boot's CBMM console. That will be a little bit more useful for firmware, as it's a little more lightweight than our proposal. So I'll jump into the BF log header structure and talk about that. So for this structure, we have 8 different fields that we're having that's in it. First, which is the version for the log header. So if we make changes to the log header structure in the future, we could just update this number. Then we also have a size field. So this is how much memory this log structure is taking. Allow for backward compatibility if other fields are added. Then we have the producer. So who is generating the log messages? Is it the firmware? Is it the bootloader? This is a null terminated string, and the length allows for ASCII UUID storage. After that, we have the log format field. This explains which format is being used to record the logs. As I said before, it could be the BF log format, it could be CBMM console, it could be something else. Various producers are allowed to not just stick with one logging format. They can use multiple different formats if they need it. So that's a null terminated string. And then we have the flags field from there, which is a bit field for storing information on the log state. We currently have bit 0 as if the log has been truncated. We're still trying to discuss on what other flags will be useful to include in this field. Continuing, we have the next BF log header address. This what makes the structure a linked list. So it's a physical address pointing to the next BF log header structure in the chain. So the first element of this linked list would probably be the latest boot component in the boot chain, so what comes right before the OS. And then the last one will be what starts the boot chain, so probably the firmware. And then since there's nothing that comes before that, we'll have it set to 0, making it the end of it. And then we have the log address field, which is quite important because we need to be able to point to where the log buffer is being stored in memory. So we have that. And then after that, we have the log size field because we need to know how much memory to read in order to obtain the log buffer. So now we're going to jump into our BF log format structures. So first of which is the BF log buffer. This is the header for all the log messages. Consist of 5 different fields. First of being version. So if we make changes to the log messages structures or this log buffer structure, we'd update that. Then we have the size field. So how much allocated space is being used by not only the BF log buffer, but all of the messages stored in the messages field. This way we can allocate it all together in one spot. Then we have a kind of a duplicate of the BF log headers producer field. The reason we're duplicating the producer field is because we want this to be independent of BF log header. So we can detach it and still have all the useful information for reading this, but we don't need to rely on BF log header as much. And next we have the next message offset. So it's a byte offset from the beginning of this structure all the way to the next available byte within the messages field. So as we're storing more messages, we'll increase this byte offset and then we know where to put the next messages as they come in. And then lastly, we have the array of log messages stored in the BF log message structure. Now, for each individual message that will be stored, we have the BF log message structure. So this consists of 7 fields, and first of which being the size, so how much space this log message entry takes up. Then we have the timestamp in nanoseconds, so when the message was sent by the producer, and the producer would define what it believes the meaning of 0 would be for this log format. Next, we have the level field. So it's similar to syslog in that it is used to differentiate normal logs from debug log messages. And this is up for producer interpretation, as well as facility, which is also similar to syslog meaning and is used to differentiate the sources of the log messages and where they're coming from within the producer. Continuing, we have the message offset field. So this will be used to specify where message is starting in the structure because the type field isn't determined at how big it is. So we don't know when the message field would necessarily start. So we have to specify, okay, which byte in the structure is it starting at? So that's what the message offset field's for. Then we have the type field, which is the log message type. And it's similar to facility, but this is a null terminated string instead of an integer. Now it's the case that the producer can use either type, level, or facility, or any combination, or it doesn't have to. So if that's the case, it can set level and facility to 0, or it can set type to an empty null terminated string. That's up for the producer to decide. And then lastly, we have, of course, what we're storing, which is the log message, which is a null terminated string. So an example on how we got this set up on the grub last year, we had it so that the logs would be read directly from the grub printf functions and then stored in a temporary buffer, which would then get dynamically reallocated. And once this has happened, the log would be copied into a final spot in memory and then passed to the Linux kernel through some boot parameters, where then the user would be able to parse it using parsing tools after it's been exposed. Within the bootloader, we had a couple of environmental variables to be able to control the usage of the log. So we had the grub log environmental variable, which would turn on and off the log if it wants to record or not. Then the grub log debug variable, which would allow for debug messages to be recorded. And then the grub log debug FL variable, which would allow for file and line numbers to be recorded in the debug messages. Here were some of the changes we needed to make for the Linux kernel in the boot parameters. So we had to add a bootloader log address parameter, as well as the log size, because we need to know how much we're reading. So those are some of the changes we need to make the log work in that scenario. Now, some topics for discussion is the specification placement. We're not entirely sure where to put it. We could make it a part of an existing specification, such as in Uefi, ACPI, or Multiboot 2, or we can make it standalone in the case of OASIS standards. So this is up for discussion, along with how we're going to pass the log to the OS. We could either, well, on Uefi platforms, we can use configuration tables to pass the log. So once we pass the log to the config table, the Linux kernel would look through the config table, and then it would expose it through a file path such as the one shown on the slides. In the case of ACPI and device tree platforms, we could expose it using the next log address field in the BF log header to pass the log. If none of these scenarios are on the platform, or none of these platforms are being used, then it becomes a little bit trickier, but platforms that don't use Uefi, ACPI, or device trees are becoming less common, so that shouldn't be too much of an issue. So some previous discussions, we have links to them here you can find in the slides. We also made a couple of patches to the grub to allow for bootloader support and Linux kernel to allow for bootloader log support. We also created a log parser known as slstat tool, which should be useful. Now, a couple questions that we do have for discussion that I don't have in the slides currently is if you think that it would be better for these logs to be targeted for a specific targeted format. So like if it should specify for a specific boot component or something like that, this would make it less bloated. However, we could also just make it more generic, and this would make it a little bit more flexible. Or we could, another case is how we want to pass the logs to the OS. If we should pass them all together, or if we think that just leave it and have each log or each type of log format pass it on their own. So those are some things that were also for discussion based on some of the comments we've already received. So I'll open up for questions if anybody has any.
Hi, I have a basic question. So I'm
Yes.
trying to understand how do I compare this new log mechanism with there's already TPM firmware logs in which you measure the boot chain and the config data also, and as part of measured boot. So how does it differentiate with that? And second thing is, it seems to me more like something what syslog is. So, but containing all the components from.
Yes, the log for TPM is completely different thing than thing which we are proposing. The log buffer which we are proposing here is to store messages from the events which are happening during, for example, firmware startup or bootloader initialization or memory allocation, etc. So this way you will be able to get from this to get information from this log what were happening during the firmware and the firmware runtime and the bootloader runtime. This is not targeted for system measurement or something like that. This is just to store the information. Like you said, we can compare it to the syslog thing.
So
That's
then sorry.
Go ahead. Sorry.
The ownership is that, so the log gets created starting at the firmware, and then the ownership gets transferred at every layer so that every layer can update and modify.
Excuse me, I'm not sure I understand the question.
So the log actually starts when the firmware starts. They update it, and then they pass to the next layer bootloader, and the bootloader passes to the OS, and each layer has an ability to keep modifying the log or updating that string.
The idea is that every component in the system creates own log. Potentially, of course, you can, for example, you have a firmware which creates a log, and after that passes the control to the bootloader, and then the bootloader attaches own messages to the same log buffer. But I think this is not the best solution. We think that every component in the boot chain should create own log and attach it to the buffer log header, and in this way create the list of logs which were produced by various boot components. I think that this is a better solution.
Okay. Yes, I think I'm trying to understand exactly how it
Okay, no worries, no problem.
Thank you.
You're welcome. Any other questions, suggestions?
You mentioned.
I mean, I guess regarding.
After you, Stuart.
I was going to say, regarding the question about, who passes these to the OS. I mean, I think it's going to have to come from one entity, because like on ARM systems, there's going to be several layers of firmware, before you even get to Uefi, for example, trusted firmware, perhaps secure world firmware. And so if all of these create logs, they're not going to have any way to pass them to the OS, for example. And so I think, they need to pass them to the next component in the boot chain, and eventually they're all gathered together and passed to the OS. So I think to that question, I think, yeah, you need some way of having one entity pass everything that's collected.
Yes. Yes, that is why we are thinking about various solutions. As Alex said during his presentation, we are considering Uefi, but we also have non-Uefi platforms. So we are thinking about ICPI and other platforms. But as you said, each component should pass in our design. Each component, lower component, should pass to higher level or logs produced by ourselves, and also logs produced by earlier stages. So this way, it will be easy to pass all the logs just pointing to one structure.
Right.
It is, I think, it is much easier than inventing new mechanism to pass every log from every stage in the system.
Yeah, that's that's kind of my key point.
Okay, thanks a lot. We get some comments. Sorry, Mark. Sorry.
I'll let you finish first.
Okay, so go ahead.
Okay, I was going to say for x86, you mentioned putting stuff in the header, and then you mentioned for EFI case, discovering this for a system table. You mentioned somehow that was going to be discovered for device tree and ACPI. I was going to say on ARM64 on Linux, if you're trying to support that, we obviously don't patch the image header at all. So the only mechanisms we have for discovering things are through EFI system tables or something placed in device tree. But I think, as Stuart mentioned, we've got a load of boot agents that run before that. And also we don't necessarily have like a device tree a system might not have a device tree until the bootloader creates it immediately as part of the ARM64 Linux boot protocol. So we don't necessarily have a consistent location in which to identify the presence of this table throughout the lifetime even of a single boot. To try this probably requires a fair amount more thought as to how that's expected to be transferred and discovered at each layer, because the mechanism might not be the same between, say, TFA and grub. Sorry, TFA and EDK2, then EDK2 and grub, and then grub and learns, and so on and so forth.
Okay, I understand what you mean. I think that we should be able to specify how all logs are passed to the operating system. I think that I agree that it will be difficult to specify how every boot components passes the logs from one to another stage. But I think that we should at least try to specify how different mechanisms in different platforms are used to pass, let's say, bootloader log from the grub to the operating system, and that is why we proposed at least Uefi solution. But I think that we should have various alternatives depending on what kind of system we are using.
So I think having a single way to do things is nice and all, but there are like existing ways in which this information is passed, for example, for TFA. So where we don't necessarily have the facility to grab that information. So there is also going to have to be working with those existing standards as well.
Yeah, sure. Peter, I think that you had a question.
Yeah, but I think actually Mark covered it all.
Okay. Thanks. Any other questions? I think that to some extent, I have a feeling from the discussion on the mailing list that some people think that it is not worth making such standard, because I heard, for example, that our buffer log proposal is a bit too bloated. But from after some thinking, I think that we have two solutions. Alec also was mentioning this, that we can make something generic which can be used by various boot components, and this way, of course, it will be to some extent too bloated. But on the other hand, we are able to use one standard and also create one tool which is able to parse various logs from boot components. So you don't need to create a specific tool for each component. On the other hand, if you do not like this solution, I think that we can go into something which is more targeted for various boot components. For example, grub will use own format to pass logs, and other, and the core boot will create logs in different format. So I think this is important question before we continue to reply to this question, before we continue the work on this. Of course, Alec will be replying to all these questions, and I think we will continue the discussion. But if you have some suggestions right now, we are happy to hear that.
I guess one other comment is, I mean, I have heard some discussions around this in the context of BMCs. So, you have a server system with a BMC. In some cases, there's ways the BMC, which is does management functions, can collect logging and boot status codes. And I don't know, I'm not sure where those discussions stand as far as, like, say for ARM, trusted firmware logs being accessible by a BMC. But it seems like some of the same problems might exist. And so I don't know, it's probably worth just understanding whether or not there's any current BMC related, log collection mechanisms that, either may exist or being worked on by, people in that community, like maybe OpenBMC or something like that. But just a thought that it's another place where logs might be useful. Okay, makes sense for me. Stuart, could you give us some contacts for the people who are working on similar thing for BMC? Yeah, there's someone I know who, let me just see if he knows, and I could I could let you guys know. Okay, I don't know right this minute, but okay. No worries. You can send me an email. Yeah. Any other questions, complaints, suggestions? Okay, I think that we are done. Oh, James, sorry. James, go ahead.
I was just going to ask the obvious one about logs that we actually want to be attested versus logs that we don't. Are we going to try and split the log format to do that? Because obviously there are things that we would like to see in the boot log. And to do that, you're going to have to be in the TCG log format. I don't remember if we do it via verifiers, but we could do it via the logging system as well. I'm not sure I understand the question. But it's not a question, it's an observation. There are certain pieces of the grub log that are important for security terms. And those important pieces should be verified, I think, through the TPM if you're doing measured boot. So are we going to have a way of routing the log into the TPM boot log?
We didn't consider that, but I think that this is very good suggestions. I think that it shouldn't be very difficult to introduce such mechanism into the graph. I think that we can do in similar way, which we did for this logic mechanism. So I think it shouldn't be very difficult. It requires Alec added the code which does this logging. I think it doesn't require more than 100 lines or something like that. So it shouldn't be difficult to do measurements of some logs from the graph, I think.
Okay, thank you.
You're welcome.
I believe I missed some piece, since we still have time left, right? I believe I missed some piece on why are we trying to boil the ocean? Like, do we really have any platform out there that is not Uefi that you care about? Maybe some BIOS platforms on a VM, sure, make a one-off there. But do you have something that doesn't deal with basically GUIDs that tell you I am table XYZ, and then you just ingest all of these tables, and every time you find identifier X, which means I'm a grub log file, you just expose them using sysfs?
So do you suggest that we should just care about Uefi stuff only? I think that Piotr could say more about that because he works on firmware worlds, and I think he can say something about that.
Yeah, so currently, like, market share of laptops is 10% Chromebooks. All of them are core boot.
Core boot has its own mechanism to transmit arbitrary data from core boot into the OS, right?
Yes, but core boot also may want to use grub-based booting. So why grub should not support core boot mechanism, or just agree with core boot community how to lay out the logging format?
Sure. Again, it's about boiling the ocean. If there is a core boot incentive to implement that, then we can literally just shove it into CBFS, can't we?
In general, core boot. Sorry.
Right now, there is already mechanism. There is CBMM, and if you look at the thread where this RFC version 3 is discussed, Julius Werner from Google, his Chromium firmware maintainer, already kind of pointed his opinion about that. So and I believe Daniel repeating his opinion that this spec is bloated, and he's got a couple other points precisely saying what's going on around the spec and why maybe they don't exactly like it. So
okay,
so there is interest from the core boot community. This is not like they do not participating in. If I'm looking at the replies, I see for the version 3, I see 3 replies and 2 coming from open source firmware community, from core boot community.
Okay. What I'm hearing is you could very easily get away with a firmware-specific backend that just propagates a standardized file format that is grub specific, or maybe even just plain text. Literally, I don't think you need anything more than plain text in this case of what I read, what I saw here. You could pass that using a firmware-specific mechanism, such as Uefi table, or if you are not sure what you want to do for a BIOS system, maybe you can just literally ask the ACPI consortium whether you can reserve one table format, and then just make it a table, a literal ACPI table that just happens to contain plain text. And for core boot, again, like whether it's CBMM or CBFS or whatever other native mechanism the core boot people have and consider on vogue is an implementation detail. But it's like just use whatever your firmware mechanism has and make the rest on top of it as easy as possible. Put an identifier, make it a generic mechanism that just says this is a plain text file. Put an identifier on top that says I come from grub, so that somebody else can say I come from some other component in my boot chain, and you basically solve 99% of the problem with like super simple modifications.
So you suggest that we should simplify the structure which is used to pass to, logs from one state to another, right? This is my understand correctly?
I'm saying use the firmware native mechanisms you have to just own a particular grub thing and just open the door for others to implement their own, but don't do their work for them.
Okay.
As long as your format, as long as you just reserve a GUID or a identifier, and you just make sure that you have another identifier that says I come from grub, and then everything beyond that is just grub native and grub proprietary, whatever. Well, it's not proprietary in open source world. Grub specific data, you're basically set, and then you don't have to go and coordinate with every single entity that is out there. But you still have a mechanism that allows other pre-boot firmware pieces to also pass information, because you can have 5 of those tables if you really wanted to.
Okay.
Daniel, can you kind of explain like the underlying problem that you're trying to solve? Because that's I believe like that's probably something that was solved, or we just trying to unify.
There are currently, as Alex said at the beginning of his presentation, the idea of this log was created, let's say, when we started work on the Trenchboot project, and we wanted to know how the platform was initialized before running the MLE. So that is why we wanted to know what was happening in the graph. And after some thinking, we realized that maybe it makes more sense to prepare something which is not Trenchboot specific, but more generic and can be used by others. I am aware that we cannot create something which will fit all sizes. Okay, I agree that, for example, for Koboot, this format in current state is not usable because it is too heavy. That is why we decided to split this in 2 parts. One part which allows us to link all logs into the list and point to the and to have one let's call it one handle to the all logs. And another part of this, maybe it is not clear for our email from the presentation. Maybe it is our fault. Another part is thing which specifies format which can be used to store logs about what is happening in a given boot component. I think that we should split these 2 things. So I agree with Alex that we should use as much as possible existing mechanism to pass the information about logs. And I think that Uefi config tables is a good example. Alex, do you agree with me?
So fundamentally, the only problem we actually need to solve is being able to pass things up from the earlier parts of the stack to the kernel and have them in an identifiable order.
Okay.
That's the only problem we have to solve. Everything after that is stuff we want to solve, and we can solve piecemeal, but we need to make sure that we understand how to put them together once we solve them individually piecemeal, right?
Okay.
Yeah, and James mentioned the TCG TPM event log, and I believe this kind of sounds like it fills the need, because if the measurements of the stages are there, then we can figure out based on the event log that what happened before. Of course, this have to be reasonably trusted, and that's trustworthy, and that could be some problem.
Okay, we are running out of time. No, thank you for your discussion. I think that if you have some concerns, complaints, or ideas how to solve that, your comments are welcome on the mailing list. I hope that will speed up the work on this, and I will not reply after a year for the questions. So Alec, once again for a presentation, and we'll be replying for questions on the email. I think by the end of next week.
Thank you.
Thank you. See you. We'll start next presentation in 5 minutes. Stuart, you are presented right now, and we'll start in 4 minutes. Just a reminder, I would like to make you aware that we have 1.5 hour free for discussion after the presentations. So feel free to propose some topics to discuss, and we can schedule them. Okay, let's get started. I would like to welcome Stuart. Stuart is working for ARM, and he will be presenting Linux and DRTM on ARM. Over to you, Stuart. Thank you.
Thanks. Hey, everyone. I'm Stuart Yoder from ARM, and I'm a system architect, and have been working on DRTM on ARM. And so, there's been some demand for that from some of our partners, and so I've been over the last year or so working on architecture. And so we're getting at the point where we're going to have a beta spec soon that'll be public. And so there's a few questions I just like to discuss that impact Linux, and so that's kind of what we're going to talk about. So I'm going to probably spend 5-10 minutes just on just one, like what is DRTM, is just a very quick summary of just to kind of get to the essence of what DRTM is trying to get at, and then show how that maps on ARM and kind of what our basic strategy is for how we're going to do it, how it maps onto the ARM privilege levels and so on. And then there's several kind of questions I'd like to discussion points to kind of talk about after that. So that, I guess let's start. So so at DRTM, just at a high level, the essence of it is that you have one component, maybe it's a bootloader that wants to launch or start another component, for example, an operating system. And so you have this handoff from one to the other, and the typical way that you have security and you can ensure the integrity and authenticity of your OS kernel is, for example, doing a signature validation check using digital signatures, or perhaps measuring it into a TPM. And so, but in that scenario, you're relying on the boot component to be trustworthy, to be able to make that measurement or make that verification check. And so the way we typically deal with that is a boot chain, where you start in an immutable root of trust. You go through stages of boot where each stage verifies the next, and eventually you get to your OS kernel. But I guess what happens is you're really relying on that each stage of this boot chain has integrity, and there hasn't been a bug that compromised your verified boot flow and so on. And especially with something like Uefi, which is arbitrarily extensible, in spite of the fact that it has secure boot and verifies all loaded drivers and so on, there's just still, the bigger this chain gets, the harder it is to rationalize that there hasn't been a compromise somewhere. And so getting back to our boot component wanting to launch the target image, what DRTM gives you is the ability to have a higher privileged root of trust that verifies or actually measures your target image before executing it. So that's what we call a dynamic launch. And so you're going to initiate a dynamic launch. You'll have to take a measurement of your target image into the TPM, and then you transfer control to your target image. And so then with that measurement, that OS kernel or whatever it is, hypervisor, can then enforce a security policy around that measurement. If that measurement isn't correct, like what was expected, then you could either halt boot or do whatever remediation is necessary. So that's the gist of it. You could also, it's not necessarily just from boot to OS. You could have one OS image start another one. So like, for example, kind of like a kexec. And so this is not a boot time only mechanism. So how do we map this onto ARM? Actually, sorry, one other thing. So the other thing that DRTM gives you is some security guarantees. And so here, basically what DRTM guarantees is that you have a trustworthy measurement of your target image, and that when you start executing it, you're in a safe state. There's a single threaded execution on the system. There's no interrupts enabled. There's DMA protections in place that can guarantee you're not being under a DMA attack. And that also there's some data provided by DRTM so that you know what your physical memory map is. There's some security critical ACPI tables that are provided as well. So you start in a safe place essentially, and then that OS kernel can go from there as it kind of builds a new TCB. So mapping this onto ARM. So on ARM, there's like ARM v8, 64-bit architecture has 4 privilege levels. And there's a secure and non-secure division there. So on the secure side of an ARM machine, you have this secure firmware at EL3 and the potentially secure OSs that offer secure services. And then it's in the non-secure world where, like Linux and your normal application type OSs work. And so the scope of DRTM on ARM is about the non-secure side of the machine. So we're not trying to relaunch everything, but it's how in the non-secure world can you launch your hypervisor OS kernel securely. And so what that looks like is shown in this flow here, where in this picture here, what I highlighted as the DCE preamble, which is where things start, is your component that wants to launch the target OS kernel. And so that, in this example, is at EL2. And so an example might be wanting to start Linux or trench boot. And then the DRTM implementation begins in our EL3 firmware. And so, so that's where things start. And so one implementation is that essentially our secure firmware is the root of trust. On x86, the dynamic launch happens via special instructions, but on ARM, it's going to be via an SMC call that transitions to the secure firmware, and then it can start from there. We also are allowing, in the architecture, we allow for an implementation where you start in the same way, but that the actual root of trust is in a separate security coprocessor. So there's a firmware-backed DRTM flow, where your root of trust is your secure firmware. And then there will also be a hardware-backed flow allowed where your root of trust is a security coprocessor. And so there are basically 3 phases where you start here with what we call the DC preamble, and then you do your dynamic launch, transition to your implementation, whether it's in firmware or in a security coprocessor, and then you can continue with a part of the DRTM firmware, like at EL2, and then from there to your target image, which we call the DLME. So it's a pretty simple, conceptually pretty simple flow that, where you start, you initiate the launch, and then you arrive at your target image and go from there. So that's the quick overview of what DRTM is and how we see it mapping onto ARM. I guess maybe a pause for any questions there before we jump into some of the discussion points. Okay, so there's several,
Stuart?
Yeah.
What are DCE, DLME? I know what, so CRTM is probably the constant root of trust, I suppose.
Yeah,
but
it's DCE stands for Dynamic Configuration Environment. It's basically just a secondary stage of the DRTM firmware that is going to measure the DLME and start, which then starts the OS. So it's the DLME, the Dynamic Launch Measured Environment. That's the part that gets measured where things start. So it's that code that starts in that secure place. But the black boxes here, which we call the DCRTM and DC, are just going to be DRTM firmware components that are handling, making sure things are in a secure state, taking the measurements, and so on.
Okay, thank you.
I have a question. Why did you separate the DCRTM and DCE?
Why did we do what?
Why did you separate the DCRTM and DCE?
Okay, so I mean, the main reason is that you could really combine them, but there's just a principle that we like to follow in pushing out as much of our EL3 privilege level as possible. And so that would be, combining them at EL3 would be valid, but then it just, I guess what we're trying to do is minimize the firmware at that privilege level. And so, so this is an implementation. This is not, what I'm showing here is like an example of how you could do it. The architecture does not require it, but I think that's how we see it probably in our proof of concept or reference implementation that ARM's gonna, will put out. The current plan would be to do it like this, to split out as much as possible from EL3, just to minimize, the.
Okay, I understand, but shouldn't the measurement of the LME happen in EL3 from security point of view?
Well, if if in fact you are, if you start at EL3 and if you measure and take and signature check the DCE and you're running on a single core, there's no DMA. I mean, it shouldn't be possible for the DCE to be compromised or attacked because you are measuring it and you're also requiring a signature check on it as well. And so since we were starting a small new boot chain here with this extra component, but so I guess in my view, from a security point of view, the DCE can safely measure the DLME because of the state of the machine.
Okay, makes sense for me. Thank you.
So I guess what I wanted to discuss is a couple of points about one is this handoff to the OS, and so in this case Linux. So one of the things we do is when you hand off to your target, which say it's going to be Trench Boot or Linux, is there's a set of data that we provide. I think this is in line with what is done on x86. The things we provide are shown in the diagram here. There's a list of what memory is DMA protected, so that the target image knows, like when it starts, it knows where the DMA protections are. There's also an address map of the system that shows you where where your physical memory regions are, so that you're not relying on, say, a Uefi provided address map. There's also the event log from the DRTM events, and also a set of ACPI tables that we are deeming security critical. So where the SMMUs are on ARM, PCI config space, MADT for interrupt controllers. And so there's a small set of ACPI tables that are provided that DRTM guarantees are correct. And again, so you don't have to, you can replace the Uefi provided ACPI tables with these to kind of, as you get started in Bootstrap. So I guess the one question I wanted to raise, a discussion point, was around just what, whether there's anything anyone sees here, especially from the Trench Boot Linux point of view, that might be missing, or is there anything that you see here? I don't know today what Trench Boot does as far as using ACPI tables provided by TXT, or verifying the address map. But yeah, I just wanted to at least raise the question about this handoff to see if anyone had any any points of discussion on that.
I have a question. How your implementation is close to the TCG specification, DRTM TCG specification? Because, for example, if you look at that Intel specification, it is in some places it is completely different. One good example is information how the TPM log is passed. As far as I can tell, in Intel implementation, it is passed in Intel own structures, but TCG specification says that DRTM implementations should use a special table to pass information about the TCG. So the question is, this is a good example of the
Yeah.
differences. So how many differences is in your implementation in comparison to the DRTM?
I mean, I would just say we loosely, follow the the conception. It basically conceptually follows that architecture, but when it comes to data structures and so on, we didn't use anything from there. So in this picture here, in this set of data that gets passed, we have a header that points to these different regions. And so in one region, we have the DRTM event log. We have a set of ARM unique event types and so on that were needed, but we didn't follow any data structures from the TCG spec. I mean, I guess it just didn't look like it was worth doing, and also, like you were saying, it looks like existing implementations of DRTM did not follow that spec either. So we just did what we thought made sense, rather than being picky about following that spec, because it didn't seem like there was much value. I mean, there wasn't like existing code that we're going to get to reuse by following that spec. So yeah, so we loosely followed it, but not down to the data structure level. This event log, it is a standard TCG event log, but yeah, you'll find it. The DLME will find it, through this data header. The other topic is kind of a bigger topic that I don't think we're going to solve here, but I just want to raise it. And that's about Uefi runtime services. So in this boot flow, the one thing that's is kind of missing with DRTM is that Uefi runtime services, which came from the previous stage of firmware, is not measured, right? We've measured the DLME, their target image, but Uefi runtime services is needed by the OS, but it's not measured or verified. And so one of the feedback from one of our partners, who's done DRTM on x86, just says that he sees this as a huge security hole in DRTM, and that there is going to be unvalidated code, unverified code that the OS depends on. And so this is not an ARM issue. I mean, it exists on x86, and so on on Windows, Microsoft addresses this by sandboxing by sandboxing the runtime services at a lower privilege level, along with their I mean, they have a hypervisor at the highest privilege level, and then everything else, including the Windows kernel, is sandboxed at a lower privilege level. And so that's how they deal with it. But for Linux, the question is, what do we do here? I think I've discussed it with Ard, and he mentioned PRM as maybe having a similar issue. And is there a way we could run runtime services at a lower privilege level and sandbox it somehow like that? Or I don't know, is there some way to measure it realistically? I mean, could we? The only thing I can think of there is maybe somehow split runtime services into a separate image that doesn't really get executed until the OS maybe initializes it or something like that. And so you measure it. I'm not sure, but I just wanted to at least raise this question to see if anyone has thought about it, or has any ideas, even at a high level, about how we deal with this in a Linux environment.
So to me, it thinks like it is a very similar question to what people on OSFW Slack dealing with about how to separate runtime services. And there is quite a lot of ideas. I already posted in the chat 2 Linux boot documents where they have a bunch of concepts how this can be done. There are even some mad one, like running this in VM or something like that. but I believe it is worth looking at those documents. And there is this this channel, Stuart. I know you are on the Slack.
Yeah.
There are a lot of people like fighting around that, and maybe that's good community to try to throw a question at them. And I believe Daniel probably will have way better ideas.
Stuart, I think.
Yes.
Oh, sorry, go ahead, Daniel. I'll talk afterwards.
All right, thank you. So yeah, so I'm one of the ones that was bringing up the issue of the firmware, right? It's one of the problems we've long struggled with the DRTM environments. At the end of the day, we have capabilities and things like AMD that get disabled by OEMs that would allow us to do this exact kind of containerization. So, but yeah, at the end of the day, it's Microsoft went down the same path, right? You're going to have to containerize your firmware somehow. But just like the reason why it gets disabled on AMD is that the OEMs don't want to do that. They want to be at that highest privilege level. And so, the challenge is you're going to have to strike a balance with the OEMs on how you're going to get them to be okay with being in a privileged environment.
Okay.
Sorry, all I was going to say is that I believe it's the same problem with AML. Because any AML which exists could have been tampered with by the prior OS. And even though that is somewhat sandboxed, it still has the facility to poke things in ways in which we do not understand.
Sorry. So yeah, I think by far, AMD is the one that I'm most impressed with in the way they did in the containerization. It's Appendix D inside of their system guide. So as far as I can tell, I don't think even AML would be able to break out of that containerization because it uses the hardware virtualization to containerize the firmware.
I think the point I was trying to make is that even if you containerize this stuff, the reason you're invoking it to begin with is another piece of hardware, right? And if you don't know how the piece of hardware is going to respond to that code doing arbitrary things, then it doesn't matter if you put that code and give access to the device, because poking that device may have an impact on your system.
So, okay. So that becomes a rabbit hole, though.
I think that's what
I'm sorry, go ahead.
Sorry, virtualizing things is certainly a good idea. And I think, as Stuart mentioned, Archbishop has looked at doing this in the past on ARM64, and we have ways in which we could, in theory, put some of these things into like virtual machines and more less privileged context. But the big thing is you just can't reason that it's secure.
Well, but I guess, Mark, if so the one way a device could affect you by this code poking it would be like DMA, but we have mechanisms for that, right? So we already know how to safely assign devices to VMs, and so wouldn't that address that? Or?
Sorry, but the reason that you're normally poking, there's a difference between the assignable interfaces of devices, the virtual machine assignable interfaces, and the sorts of things that get poked by firmware, right? Because like what you assign to a VM is normally like a PCIe virtual function, or like an MMIO device where it doesn't do DMA, or it's constrained behind it, an IMMU or something like that. Whereas the sorts of things that AML is normally poking, things like clock controllers and power gates and whatever. So it's very easy for this so you can't really containerize it in the same way.
Yeah, that's why I was saying you start running down the rabbit hole, right? Because the fact is that we don't have any trust mechanisms for a lot of our hardware in place that we can say, oh, I know my hardware hasn't been tampered with or block that tampering from happening. So, I've participated in some committees that are trying to drive trust into hardware, but until we get something in place, all we can do is the best we can do is containerize what we can understand what has more risk than other things, and system builders and system designers need to take those things into account.
We have about 5 minutes left. So there was one other topic I wanted to raise, which was just a point about how TPMs have to be implemented on ARM. So one key thing about DRTM is that the TPM, say you have a discrete TPM chip, can't be directly accessed by Linux, for example, because there's dynamic localities that have to be protected and resettable only by the DRTM implementation. So whether that's by DRTM running at EL3, like in this picture here, or whether it's in a coprocessor or something, we have to have a way that access to the TPM is mediated. And the way we do that typically on ARM, you'll see on ARM servers, is that there's a TPM service running at secure EL0 that offers like a command response buffer interface, and it proxies commands to the physical TPM. And so right now there's not really, this is done today. So there are some examples in the Linux kernel of a CRB driver that uses an SMC call based interface to send commands. But I think the thing that's missing right now is any concept of localities. So there's no way to express, like via the SMC call method, what localities is accessing the TPM and so on. And so, and also I don't think there's a way today that the CRB buffer can be allocated by the kernel. The way we see it, what we want it to work is where the TPM driver allocates a CRB and then tells the service where it is, because this is normal world memory. And then they can share that buffer to send and receive TPM commands. So I guess the question I have is whether anyone who is familiar with the TPM driver infrastructure sees an issue with allocating a CRB in this way, where we have the TPM driver allocate the buffer, which there's not an example of that today, but I think that's how we want it to work. And so I just wanted to at least raise this as a question for TPM Linux experts.
But why would you do it this way? The localities are designed to work so that it's only accessible from, you have 3 levels, you just make individual localities accessible from each level. Each level can have their own driver and they can touch the TPM separately, so we wouldn't need to do anything in Linux to fix it for this, except let it know which localities it can't use.
Yeah, so with respect to localities, I think, I don't see a big issue there where you're right. So I think say like a locality 4, for example, which we definitely want protected, Linux will not be able to access that locality. I guess, but the question about say just at locality 0, what we want is for the CRB for locality 0 to be allocated by Linux in Linux memory, and then the address of that buffer being shared with the TPM service and saying, okay, here's where you need to, this is where the CRB is, and then those 2 sides use that shared memory to communicate. That's what's new. I don't see an example of that, and I'm wondering if there's any conceptual issues anyone sees with.
Can I just ask why that needs to be dynamically allocated? Because I understood that one of the reasons for statically allocating this today was that it simplified all of the secure side, because you didn't have to dynamically go and change like the translation tables and whatever that had to go and provide access to that mapping.
I guess.
So what's the reason to need to do it dynamically?
Yeah, I guess. The reason so there's this framework called FFA, Firmware Framework A, which is a way that we implement secure partitions and secure services. And so in talking to Achin, who's the architect here at ARM on that, the natural flow there is that the client allocates shared memory and shares it with the service versus the other way around.
So that's true for FFA, but this isn't FFA, so why does it need to follow the FFA interface? This is an existing standard, and it's already implemented.
Well, I guess what we're trying to figure out is how can we map CRB onto FFA, right? If FFA is the transport between Linux and the service, I mean, what we want is to do that. Is we want to use FFA as the underlying infrastructure to send TPM start requests. And so the natural way to do it would be, using a client allocated buffer. So that's the question.
So one of the things I would say is to take a step back, and I think maybe this is what James was trying to get at, was that localities is meant to be a hardware authentication method. It's a way for the hardware to basically say the TPM is now allowed to be accessed in this locality. I mean, and this goes back to our discussions in the spec. Brings up a good question: is there ever going to be a time when you're going to exit your secure mode like you can on TXT? If not, then as soon as you've finished your DRTM, you're now in the dynamic. You're in the dynamic system at this point. You've done the dynamic authentication with the hardware, so you should be able to enter locality 2 and just leave it in locality 2. You'd have access to everything you have in locality 0, and the fact is you are in the dynamic runtime. So all your operations should be from the state that the hardware is in the dynamic runtime, and no need to switch localities at that point. And then if there's reasons that you want to restrict access, then that would be the responsibility and the driver that's interfacing it. So if you want to restrict application interfaces, that would be a responsibility of the Linux driver to restrict access to commands or interfaces within the TPM, within that locality.
And then I think the other thing is we actually have a spec that's not the TPM spec, but it's the TIS spec that actually allows you to share access to an individual locality between multiple components. It does actually have a sort of back off and an algorithm for checking if the TPM is busy and everything. We use that in those TIS drivers. So if you actually implemented that driver, you wouldn't need a shared command response buffer.
Okay. I know we're out of time, so yeah, thanks for the
No, you've got 3 minutes and you can break you yet.
Okay, I see. So yeah, I think we'll continue the discussion on that. I think the one key point is that, like, say access to locality 4, for example. I mean, we have to have firmware, or we have to have something mediate access to that, right? Because I guess typically we don't have memory map TPMs on ARM typically. Like, so you're going to have a SPI TPM or I2C TPM, and so it's not like we have hardware.
The whole of the locality infrastructure was designed to be for a memory map TPM. That's why the TIS interface specifies it. All the registers are mapped 4 times, each in a different locality. It's then up to firmware or the bootloader to protect each of the localities correctly. Is there just no way you can do that?
Actually, it's the PCH that actually on x86 that controls it, because it's a hardware authentication. So
yeah, so you need some kind of platform hardware to do that, which
right.
Most ARMs. I mean, there are ARM systems that do it. I mean, I have seen one, but there's not. We can't count on a memory mapped interface to the TPM.
I don't think
that's why
we actually need. Sorry, I don't think we actually need any hardware here whatsoever, because as you mentioned,
yeah,
like the existing interface of bouncing a notification up to EL3 means that you can implement all of that locality filtering in the secure EL0 component in that service, because it can know where you initiated the call from. So I don't think there's any hardware requirement whatsoever here. There's just some context information that we require and some policy that we require to be implemented somewhere.
Yeah. Yeah, the DRTM should signal to the TPM that it entered the hardware locale or into the dynamic runtime at that point. That's what happens on x86. When the instruction is called, the CPU will notify the PCH that it can now allow access to those MMIO address spaces for localities 1 through 4. Well, not through 4, because that's only accessible by the CPU. But yeah.
I think the one thing, however, that we might need here, which you've hinted at, is that if on other systems there are separate instances of the interface for each locality, and we're saying we might only have a single interface, we would need a mechanism to specify which locality we're targeting within that interface. Is that a correct statement, or if I misunderstood entirely?
Yeah, I think that's my understanding as well.
By interface to target locality, you mean from Linux or just in the lower level driver? Because all of the Linux drivers have a locality targeting mechanism. It's not much used.
Sorry, we just need a mechanism for it to communicate that to the TPM service running on Securials.
Well, but we already have standard mechanisms. The TIS mechanism has that.
If we already have that, the code is just on there.
All right, thanks everyone. I know we're out of time, so appreciate the discussion.
Thanks, Stuart. Hey, Daniel, I think your audio might be disconnected again because I can't hear you.
So Daniel asking me to introduce your talk. So welcome to the stage, Ross Philipson from Oracle and Daniel Smith from Apparatus Consulting. And they will be talking about Trendboot secure launch status and upstreaming effort.
Okay. You'll need to make me presenter.
That's how to do that. The question is, and if I, yeah, I have that. Just a second. Does it work?
Yep, I got control now.
Great.
All right, so thank you, Piotr, for that introduction. So yes, I'm Daniel Smith from Apparatus Solutions. I believe Ross is on the call, or is on the meeting here. So we'll do our best to cover any questions you all have. This will be pretty short in terms of the slides. So just a quick overview of where we're at with secure launch. So the purpose of this discussion is just kind of give a quick recap and then try to dive into discussions about where we need to go to finish getting this or get this moving in terms of being upstream into Linux. So if you have any questions about more of the in-depth details, we've presented a few times. Here's two conferences you can take a look at where we've gone into some detail about all this. So secure launch for Linux. So it is a capability being developed underneath the Trenchboot project to give Linux the ability to be directly launched as part of a dynamic launch. The primary focus right now is around the first launch use case, which is typically referred to as an early launch. So this is where your bootloader is going to be loading your OS or loading Linux and launching it via DRTM. So what we did and the approach to this was, instead of trying to create a whole new custom entry point to Linux, we try to reuse as much as possible and follow the standard patterns for how new entry points are added to the Linux kernel. So that's where, like it says here, we leveraged Uefi support for handling the EBS handoffs. And then on Intel platforms, we actually wired in the SExit instruction into all the shutdown paths, so that way we can control or we can properly close out the DRT or TXT, so that way your platforms can shut down nicely. And then along with that, to enable being able to do that, you need a bootloader that's capable of initiating a dynamic launch. So there is actually 2 patch sets in progress going to Grub to enable it to both launch from a Intel platform as well as an AMD platform. So in order to be able to do this, there's actually 2 additional components to launch both on AMD and Intel. One is actually directly provided by Intel, that's the Intel ACM. And then on AMD, there's the need for a secure loader, which Trenchboot is in the process of developing our own secure loader, since none is provided by AMD. They open the specification and then they leave it to the user to build an implementation. So, and then let's see. Oh, dynamic launcher locators. Oh, so at the end of the day, both Intel and AMD is in progress and going up for grub. Oh, I guess I can't use arrows. Okay. So in terms of capabilities, we've already gotten upstream. So there was the kernel info patch set that was to meet one of the needs we needed for the Linux kernel to be able to convey the extra boot information. Typically that's done with the setup header, but those that are aware, it's out of, there's very limited space and they're very cautious about adding anything new to the setup header. So we collaborated with HPRM and came up with the kernel infrastructure. Daniel Keeper, worked with him, and they basically have got that solution, or that patch set already merged. So now we're basically down to the primary secure launch feature. That leverages that, obviously. One of the issues that came up during this process is the fact that ideally you want to store the measurements as they're taken. And since the entry points into the kernel is always in the real-time kernel, the compression kernel, there's not a lot of infrastructure in there. There's a lot of it's just there, just the bootstrap to get to the main kernel, to the piggy. So in early implementations, we came up with some TPM access code that we put into there to manage that. Unfortunately, that does create two different implementations for TPM access in the kernel. So the TPM maintainers really didn't want to see that. So obviously, we were trying to work with them. Unfortunately, the TPM driver has a lot of dependencies on the runtime or the decompressed kernel infrastructure.
Question here. If I go back to Peter Jones's point that most people boot from UEFI, why don't you just use the existing UEFI driver? It should work until exit boot services, which is
exit boot services is called by grub. So in DRTM, you're required to call EBS before you call the senter instruction. So exit boot services have already been called by the time you enter into this.
Okay, but can we go back to the babies? We deliberately shifted exit boot services into the kernel and the EFI stub. Could you not do the same?
So I'm sorry, I don't follow that question. So what are we going to move into the?
Well, the problem if you call exit boot services is you'll actually lose the boot log, right? So you have to find a way of passing boot log to the kernel. Because of all these problems, we actually moved exit boot services into the kernel startup code, right, for EFI. So now we can collect the boot log and we can do everything else, but that should theoretically also mean we can use the UEFI TPM driver until we do that.
So that is why Daniel Keeper and Alec presented the log infrastructure that the firmware and boot log infrastructure that they were presenting today. That is to address that very problem, so that a way the boot log can be passed along to the operating system or to Linux. Because the fact, when you read the TXT spec, I understand what you're saying, but the fact is that the TXT spec, and there's reasons why you want to do this, is you want EBS called, you want boot services gone before you start the DRTM. Right? That's the whole purpose, because if you don't, now you're incorporating all of that stuff into your DRTM environment. Right, and the whole purpose of this is to reduce that attack surface, reduce how much we're actually having to keep inside of the trusted base in terms of what's being launched.
In addition to that, the call to senter is going to take control of all the APs, and it would leave UEFI scratching its head as to what happened to all of its control over all of the processors after it returned from senter, and we've seen like terrible crashes due to that. So that's another reason why you have to exit boot services first.
Yeah. So there's security reasons why you want to do it, and there's the technical reasons why you need to do it. So, at the end of the day, we need to be able to, and then one of the things about secure launch is obviously the whole purpose is to take measurements before you start executing. And so some of the things we want to make sure we measure as part of the DRTM launch into Linux is all of this outside information that's coming in, the boot, the command line, the decompression of the PEGI, that it's the right one, all this stuff. So we take these measurements, and so ideally you want to get them into the TPM as early as possible. But I had some discussions with a few colleagues, and they brought up the point that, for the most part, you haven't changed who's in control when you move from the PEGI to the, or from the compressed kernel to the decompressed kernel. So it is okay to just carry those measurements across, and then when you finally get access to the TPM, you could then send those measurements. Down the road, we can always, we do have a patch set where we kept our TPM code in place, so if somebody wants to use a out of tree patch, it's there. But I mean, ultimately, if we can work with the maintainers and just find a way to create a shareable code base that can be used by both the compressed kernel and the decompressed kernel, that would be the big one. But I looked at it so many times trying to figure out how I could do it, and it was just going to be major surgery to the TPM driver. It just and I mean, it's just that's beyond the scope of what we were trying to do here. So that brings us today. So we had an initial RFC back in March of 2020. We've had 4 follow-up submissions. The 4th one just posted just this past August. We've tried to address every issue that we can, or explain why we don't feel it's our view on the issue. So at this point, we're kind of like, okay, let's start talking with the maintainers, and let's see what do we need to do to keep this moving forward. Is there additional things we need to address? Is there, what else do we need to do to keep this moving forward? And so at that point, just kind of, as this is the last slide, so just any questions? I think that's, yeah. So, I mean, questions, discussions?
So I have a question on the TPM side. When you're deferring the measurements to be extended by the uncompressed kernel, I mean for the later kernel, so how the logs are being done? So when the OS Linux kernel extends to the TPM, it appends to the TPM firmware log which it had received from Uefi?
Yeah, so there is actually, so the DRTM has its own log. It's actually on Intel. It's set up by the firmware. So the ACM, the BIOS ACM sets up the log space for it, or well, sets up the scratch space, and then Grub uses it, or the preamble will set up the. When we go through as we take the measurements, we log the measurements into that log. And then when we put markers, non-event markers within the log to denote when the kernels, the compressed kernel starts taking measurements until it's completed taking measurements. So put a non-event into the log there. And so that way, when we get into the decompressed kernel, we have logic in there that basically finds the event and then walks through each log event and does the TPM extend at that point. So that way the extends will line up with what's in the log.
Okay. So, but these are not done atomically, means the log has been updated earlier itself and then the PCRs are updated afterwards, is what you're saying.
Correct. So again, it goes back to the point of this is kind of viewed as acceptable because the log is under the control of the kernel. The kernel maintains control of the system all the way through until it starts to launch the runtime. So Yes, it takes the measurements earlier, holds them to the side, and then it extends them into the TPM. So does that open a chance for a Toctal kind of attack? Yes, but I mean, with the DRTM launch, the whole point of this is that the kernel is in a very controlled state. DMA's been blocked. Interrupts have been, well, actually, the interrupts come back online. So there are some chances for SMM to potentially tamper at that point. But outside of that, you know, the kernel is in control of the system.
Okay, and I had one more question. So when the logs are coming from Uefi, I think they get copied to the kernel memory, right? After the exit boot services in your in your compressed kernel as well. That means the firmware log is no more the same what the kernel has been exposing. Is that right?
I'm not.
Probably I've not understood something here, so correct me if I'm missing out something. But what I'm trying to understand is, like, generally, currently, like, the logs get exposed from UEFI after exit boot services. They get copied to kernel memory, I think, and then kernel doesn't append anything there. But now what I'm understanding is that after they are copied, the kernel is changing it, and
So again, there's two separate logs. There's the SRTM log that's created by the firmware, and there's the DRTM log that's created as part of the DRTM process. So there's two separate logs here.
Okay. Oh, okay. And the DRTM log is what getting appended. Okay. Thank you.
No problem.
So Daniel, you mentioned that in this model, you do exit boot services in Grub, and then basically you enter the kernel, skipping the existing EFI boot stub that's used.
So again, so I wouldn't say we're skipping it. We reuse parts of it to handle some of the what do you want to say, setup from an EFI environment. Ross can kind of dive into a little bit more detail since he kind of worked all this out. But you know,
Grub triggers code in the kernel, and then you go back to Grub, and then you call exit boot services.
No. It works in that way that the Grub initializes the platform and sets up everything for DRTM initialization, calls exit boot services, and passes the control to the ACM using senter instruction. And then ACM passes the control to the kernel using a bit, I remember correctly, different entry point specified in the kernel.
Okay, so the EFI boot stub is not executed.
Yeah,
right,
exactly. Right.
So how is that not skipping the EFI boot stub?
Well, so again, it's not. So if you want to be, you know, very technical about it, very nuanced about it, yes, it's skipping it, but it's not like we're completely ignoring it. Right? We reused some of those code paths in there.
So you reuse code that's in the kernel, or you've copied that code out of the kernel into Grub or into some other code base?
I think that there's a confusion here. We are using early startup code from the kernel. We are not reusing EFI stub. So EFI stub from the kernel is not used. We reuse some early startup code, and after that we also use some code which is used to initialize the platform in the kernel proper. But I think that Ross can can provide more details how it works. But I'm sure that EFI step itself is skipped and not executed when you use the DRTM.
Right. I guess the key point is like, we didn't reinvent parsing the EFI boot table, right? That's all provided. And we reuse the code that knows how to parse that table, right? We just
the EFI boot stub is code that is executed that is in the kernel, but is executed in the boot services environment.
Yeah, no, that does not happen.
So in that scenario, we then end up with two distinct mechanisms for executing the kernel based on whether or not we're going into DRTM. And the amount of information that we've extracted from the boot services environment is then distinct between these. So as an example, right now, we have code in the boot services environment, in the boot stub, that's involved in parsing the event logs in order to be able to pass the boot services SRTM, TPM event log up to the runtime kernel. And if none of that code is being executed, so that's one example, but there are other cases where in order to integrate with the firmware, we need to basically have code that is owned by the kernel, but which is executed in the boot services environment. You're basically skipping all of that. And that means that we're going to have disparity in functionality between scenarios where people are doing a DRTM launch and where people are not doing a DRTM launch.
So the information, that information is extracted by Grub, right? There is a header that's passed.
No, it's generally not abstracted by Grub. Grub does not currently do anything to copy the, if you're right now just using Grub and calling exit boot services in Grub, then you do not get the TPM2 event log in Linux. It doesn't work. The only way you get the TPM2 event log in Linux at the moment is by calling the EFI entry point, which then executes boot services code within, that is with part of the kernel. And the TPM event log is really not the interesting part of this for the DRTM case. I'm just using that as an example of something that exists there. The kernel does need to have a fairly intimate degree of knowledge of the firmware it's booting from. And some of what we're currently relying on is in the boot stub code. Now, a bunch of this is because Microsoft don't have to deal with this because they own the bootloader and the kernel simultaneously, and they can move both of those in lockstep. But on the Linux side, we've sort of gone for, if we're adding new functionality to the kernel, we put that code in the kernel because we don't know which bootloader people are going to be using. And the presumption has been, if we're booting on EFI, we will execute the kernel's early EFI code. You're skipping that. And as a result, we're going to end up with some features that are just not going to work.
I would disagree. I don't think that's the case. I disagree.
It is extremely the case.
I disagree. I mean, we can.
Okay, so how right now do you get the SRTM TPM2 event log in the DRTM environment?
Is Russ still on with us?
Yeah, I'm here.
Okay. Are we losing the SRTM log?
I thought that's what Alex, the whole purpose of Alex's work is.
Right.
So right now you're losing it. You have a potential path to not losing it, but right now you're losing it.
Yes.
Okay. So that, like I said, that's an example. There are other cases where we are potentially going to add stuff into the kernel to integrate with a new Uefi feature where we need to have code that's happening in the boot services environment. Because you're skipping that, because you're relying on that instead, you're basically saying that when we're adding features to the kernel, we're going to have to also add that to any bootloaders that we care about. Otherwise, it's just going to be a functional disparity between the DRTM scenario and the non-DRTM scenario.
And so at that point, I would say, maybe some thought needs to be given to figuring out how this tight coupling has occurred. Should be looked at getting decoupled.
So one way of potentially doing this would be that rather than, right now the EFI boot stub is basically a thing where you jump into that, the EFI boot stub executes a bunch of code, and then it is the thing that calls the kernel entry point. So in principle, something that could be done would be, instead of doing all you're doing in Grub, do it in the EFI boot stub instead. And then just basically have Grub treat the kernel as an EFI executable, call into its entry points, and then the kernel is responsible for the boot stub is responsible for doing the secure launch of the actual kernel payload after it's done all the setup and populated boot params and so on. And then you can measure that as necessary. And that way the kernel is also aware of what data it's passing to the later stages, which is information you potentially want to be able to measure. So that would be one way of doing it. Another would be, maybe we should have some way of passing an argument where we call the EFI boot stub, but don't actually pass control to the kernel. Basically do the setup code, have the kernel be able to provide a bunch of setup code, and then have bootloaders be able to execute that setup code, but then pass control back to the bootloader, rather than having the code execute the kernel itself.
So now you're pushing two different, you're going to create a new entry point into the kernel.
Well, you're already doing that.
Right, exactly.
Actually, we don't have to do that. Oh, wait, we don't have to do that. What we can do is we could actually build the EFI boot stubs as a separate binary that then knows how to call its current entry point into the kernel. You could separately measure that binary using the standard measured and secure boot things, and we could effectively do a two-stage boot in the kernel. I mean, it's horrible, but it may be acceptable to your SRTM, your DRTM case. Would that work?
So just a bit of history. The original design was to actually do it all inside the setup, but not exactly in the same manner. But that was found not to be acceptable or doable. So I would have to go back and look, and maybe there's a different way to try to do it.
We're not proposing that you would be in charge of this. The kernel would be in charge of this, but we would separate out the code so that you could get trust for the DRTM. That's the essential key feature. This code would be evolved in lockstep with the kernel that was working on, right? So we get all the features we need in the kernel versions we need.
Okay. But, okay. I mean, I guess I would need to see more of how that would exactly work.
I'm hand waving wildly here, to be clear.
Yeah, yeah, exactly. I'm trying to think of how this would be different than what
But
outside of being a separate binary, but I mean, at that point, I mean, yeah.
I think really what I'm trying to say here is that we need the kernel to be able to provide code that executes before exit boot services. And we need, if the presumption is that the bootloader is going to be responsible for calling exit boot services, we need a way to execute that code before the bootloader calls exit boot services and does your handoff.
Right. So instead of creating a whole new binary, again, why not do that in Grub? Because there is a structure.
Grub is not maintained by the same people that maintain the kernel, and we cannot guarantee. So also we can't guarantee updates. People expect to be able to use Grub from like 17,000 years ago and still boot a modern kernel and have the modern kernel provide the set of features that the modern kernel supports. So we're not, like I said, Microsoft don't have to deal with this because they're able to tie the bootloader to the kernel. We don't have that luxury. And so a bunch of design decisions that have been made are basically focused on the fact that we need this code to live in the kernel because we can't rely on the bootloader to do this for us.
Well, also Microsoft does have this problem because they have to then evolve their bootloader in lockstep with their kernel, because what you're talking about is intimate details you're passing between something in the pre-exit boot and something in the post-exit boot. Right. And all we want is that thing to be able to control whatever needs the information in the post-exit boot. It has to be done that way.
Their bootloader basically is the EFI stub. The way they're organized, they're building their bootloader out of the kernel tree, and they just don't have the second step in the kernel.
One thing might help.
There's not an expectation that you can use the Windows 10 bootloader to, well, you can't use the Windows 8 bootloader to boot the Windows 10 kernel. That's not a thing that works. They've got a separate hands-off protocol for every kernel version, and bootloaders support that.
I think one thing that might help to think about this is the exact same problem as k-execing from an older kernel to a new kernel, where that older kernel does not have the new functionality in the EFI stub, and it has already done the exit boot services. So we must, in those cases, support a less featureful set of EFI of things that we could have got from EFI anyway. So, and also you're mentioning of supporting an old version of Grub and whatever, would be absolutely fine. You just don't get this launch, regardless of where it's built. So I'm not sure there's actually a strong argument either way for it being in Grub or the EFI stub, if you think about it that way.
Yeah, the other problem is like, again, we're trying to come up with a unified way of providing this across x86, across, and actually Intel and AMD are actually different. And then we also, as part of what Stuart was mentioning, which is we're looking at trying to get to next, is to be able to handle this case for ARM. Like, how do we don't want like 3 different entry points for 3 different DRTM capabilities. We want to have this nice, clean, single entry point for all the architectures that are capable. And I forgot Piotr's doing power.
Yeah, so actually saying that argument is actually a very strong argument for doing it in the EFI stub, because then there is one consistent interface. Whereas if you're not doing it in the EFI stub, you have a per architecture interface for launching the kernel.
So, but on power, we don't have UEFI. We typically not use UEFI on power, and we also would be glad to implement the RTM there, because everything, for example, on Power 9 seems to be there in terms of hardware. There's some missing pieces in firmware, but maybe someone can develop that. But on the other side, we would like to have some support in the higher layers, in bootloader and kernel. And it would be great to have a consistent way.
If I understood correctly, Matthew, you proposed to have a separate UEFI protocol which is installed by bootloader and which can initialize the platform for the kernel. Am I right?
I think propose is too strong a word here.
Okay. Okay.
Yeah. So in theory, we could, right now, we link the EFI setup code into the kernel.
Yeah.
And
okay.
really, what that EFI setup code is doing is making a bunch of EFI calls, which culminates in exit boot services, but that's not inherently necessary, and generates a set of data structures. In some cases, it's doing stuff like modifying boot params and passing stuff in there. In other cases, it's installing a configuration table that can be accessed later. So it's basically some code that is executed, which in 1 or 2 cases may actually touch hardware in order to deal with platform quirks. But fundamentally, we're executing something in order to have information to hand off to the kernel. And then we're calling the exit boot services and handing off to the kernel. There's nothing fundamental about that that says that that code has to be part of the kernel image. So one scenario, which I think James was suggesting, was support building a kernel as we do now, but take the EFI setup code that we are linking into the kernel and also have that available as an independent binary that basically does all of that, that generates a data structure, but which doesn't call exit boot services. And then you'd be able to call into that from Grub or wherever. Do that, have that generate all the information necessary to pass off to the kernel, go back to Grub or whatever, do your dynamic launch, but pass the information you got back from that up to the runtime kernel, and potentially measure that if any part of it is considered security critical.
So let me ask you this: why couldn't that just be done in the shim? And outside of calling EBS, have the shim worry about doing all the setup stuff?
Which shim are we referring to here?
I guess technically there's 2 of them, right? There's the Red Hat maintained one, and then there's the Linux Foundation.
So shim knows nothing about Linux, and
the answer
nothing about Linux.
Actually, the answer is simpler than that. The information we're passing is tightly coupled to the kernel version. Whatever passes it has to be tightly built with the kernel. We can't use shim because even shim's pace of development is too slow. We are talking about a tightly coupled system that we don't want to decouple because it creates an API mess.
Wouldn't it be simpler to have an Uefi protocol which has an quite well-defined interface, and this protocol could be installed by provided by bootloader handwave?
And really, the important point here is that we don't want to rely on the bootloader for EFI setup. We want the kernel to be able to do the EFI setup work. When I say the kernel, I don't literally mean the running code that is executing on the system once we're running Linux. I mean code that is shipped out of the kernel tree. And right now, the simplest way for us to do that is to link it into the kernel. But I think the actual feature request here is for there to be some way in the trench boot model for the kernel to provide EFI setup code that can be executed before we enter the actual kernel. And the precise details of that.
Okay, I understand. Okay, we can discuss this later. Okay, understand.
Okay. I unfortunately have to get going. I have to give another talk here in a moment. Any last questions for myself? Okay.
Thanks, Daniel, Daniel and Ross for doing presentation. And
No problem. Thank you.
And James and Matthew and James for your input. Okay, so I think that we are done for today. We can open the stage for any discussion related to the system boot and security if you want to.
So in light of what we were just discussing, I know Daniel Smith is gone, but in light of what we were just discussing, I mean, would a good next step be to possibly produce some sort of RFC around how to approach what was just brought up by Matthew and James, and you know, post that and get some discussions going on that? Because at this point, like someone said, it's just we're just kind of hand waving, saying, you know, this is the problem, but you know, what the actual solution is. There could be several ways to approach this.
I think that the best solution will be to meet together with Daniel and maybe with James and Matthew, have a call and to have a discussion about these issues. And I think that we have at least two issues here. One is how to properly start that trench boot on Uefi platform, and another is TPM. If we solve this, we don't have the TPM issue, I think, or have. We'll see. So my proposal is to meet and to discuss various solutions, maybe internally in the trench boot project and later with Matthew and James.
Well, I propose within Plumbers, so just use one of the hack runs. We just need to coordinate.
Okay, makes sense for me. When, James, when you are free?
Well, that's the problem, right? Because I'm supposed to be supervising the boss sessions on Friday, and this ends, I mean, basically it's now, if we can get the other guy back. But Thursday is also a possibility. I thought I was supervising a session on Thursday, but I'm not.
Thursday is much better for me than Friday because I have some family errands to run. So Thursday is much better.
I don't know about Daniel Smith, but Thursday probably won't work for me. I'm going on vacation soon, and
oh, okay.
I have so tomorrow is not going to be a good day, and Friday is definitely out.
Should we
Well, what
just
about after 11?
by email and then just sort of make sure that we have a basic understanding, make sure that we all have a basic understanding of the issues we're talking about, and then if it seems that a higher bandwidth conversation would be necessary, figure out some way of handling that.
Makes sense for me. For us,
That seems reasonable.
Actually, since you're all matrix now, we could just create a temporary matrix room for this, so you could have an online discussion.
Okay. So I think, Ross, that Ross, Piotr, and Daniel Smith, we should sit down and work on the provide some description what we want and what we need and why, and then put some proposals, and then I think that then discuss them with James and Matthew. Matthew, James, are you okay with that plan?
Oh yeah, that's fine. Get you through it straight, and then we'll discuss it.
Okay, thanks a lot. So sounds like a plan. So anything else to discuss? So I think that we are done for today. Thank you for joining us, guys, and I hope that we'll see in person next year.
It's supposed to go through the sponsor slide. Yeah.
you.